Hello, here's a bit of biographical background to Edwin Hubble, the American astronomer, pioneer of cosmology, famous for a number of reasons. I mean, perhaps no more so than having a particularly famous telescope named after him, which is orbiting around the Earth as we speak. He was born in Missouri. So for those of you not that familiar with the states of the US, this is right in the middle, pretty much. So he was born in Missouri. He then moved to Illinois, so going up towards the Great Lakes. He moved there when he was about 11. He was a talented sportsman and athlete. He, particularly in track and field and basketball. He was the captain of the basketball team at the University of Chicago, where he did his first degree. While he was at University of Chicago, he was a student assistant to Robert Millikan of the Millikan experiment fame, the oil drop experiment. He also went to Oxford University, or University of Oxford, I should say, Queen's College, because his father was particularly keen on him studying law rather than science. So whereas he had been studying maths and science and philosophy when he was at the University of Chicago, he went to University of Oxford, studied law, literature, Spanish. I mean, this is a multi-talented guy academically and athletically. He then came back to the US when his father died. So when he was in his early 20s. So he moved to Kentucky, so that's just below Illinois. So he's still staying in the middle parts of the US. And he then got a job as a high school teacher, then went back to University of Chicago to do his PhD. And he kind of rushed his PhD. I mean, you can see here, when he was in his 20s, you're coming up to the time of the First World War. The US didn't enter the First World War until 1917, so towards in the last couple of years. And he hurried his PhD to a conclusion so he could join the army and serve in the First World War. And he was fit to serve overseas in 1918, but he didn't actually see combat. He didn't get deployed to Europe actually in a combat role, but he had made the rank of major. So after World War One had ended, he then received a position at the Mount Wilson Observatory near Pasadena in California. So this was 1919. And he remained at the Mount Wilson Observatory until he died in 1953. His arrival at the observatory coincided with the construction of the Hooker telescope, which I've mentioned in one of my other videos in the waves and optics section when I went through big telescopes. And this is a 100-inch reflecting telescope. It was the largest telescope in the world at the time in 1919 and 1920s. And he started observing Cepheid variables. These are particular type of variable star. So the brightness of the star is changing in a fairly predictable way, which means that they're good to be as standard candles for working out the distance to these particular stars. So they're a good way of mapping out how far away things are in the galaxy. So he started observing these in 1924. And what he discovered was that many objects that were considered to be nebulae, as in the birthplaces of stars, these are big clouds of gas where stars are formed, and people thought that these objects were nebulae inside the Milky Way. And he showed that actually, no, they're too far away. They're not inside the Milky Way. They're actually other galaxies outside of our own. And this was completely new at the time. I mean, the prevailing view at the time was that the universe consisted of the Milky Way. Everything was in our galaxy. And the idea of there being multiple galaxies and things outside of that was just not thought of at all. This is only 100 years ago. It shows how far things have moved in the last century. Based on this, he's now discovered we've got all these other galaxies around. He then came up with the most commonly used system of galaxy classification, where you've got elliptical galaxies, so they going from being spherical to more and more elliptical. So they're getting flatter and flatter. So these are your elliptical galaxies, and then these branch out into different types of spiral galaxies. So you've got just regular spiral galaxies, and these are classified by how tightly wound their arms are. So ones that have got very tightly wound arms all the way through to ones that have got quite open arms. And then you get barred spirals. So these are your spiral galaxies. But you also get barred spirals where it looks like you've got a sort of bar in the middle, and then the arms come off of that. So you can have a barred spiral with very loose arms, this sort of thing. So this system for classifying galaxies is it's still used commonly nowadays. So he came up with that following on from these observations that he was making. Also continuing on this theme, he's working out how far away everything is. And he's got this distance analysis of galaxies, and he noticed, looking at the stellar spectra of these galaxies, he saw this relationship between distance and redshift. So he saw that the further away, or I should say the farther away the galaxies are, the greater the redshift. So if they were farther away, they were moving away from us faster. So he saw this relationship, and no one knew why this was the case. I mean, people didn't know about an expanding universe back then, or at least nothing had settled on there being the possibility of this expanding universe. I mean, it was interesting that Einstein had predicted that the universe would be expanding or contracting back in 1917 when he was working on his general relativity, and he kind of fudged his equations a little bit. He wanted to make the universe static, so it wasn't expanding or contracting. So he added in this thing called the cosmological constant that fudged things a little bit. It gave a static universe, and he regretted this later on when, based on the work of Hubble, it was shown, well, actually, no, the universe is expanding. You don't need this cosmological constant. I mean, interestingly, the cosmological constant has sort of come back in the last few decades with the discovery of dark energy and a different, the fact that the expansion or contraction of the universe is not just dictated by the gravitational effects of the matter that's in it. There's this dark energy that looks as though it's driving, accelerating expansion. So the cosmological constant is sort of come back again. But going back to Hubble, in the 1920s, 1930s, when he's doing all of this, and we're seeing, it looks like the universe is expanding. This was a new thing. This is then bringing us in to having the idea of a Big Bang, where you've got this central point. If it's expanding, what is expanded from? Where was it at its smallest point? So it's bringing us into Big Bang theory and such like. And so he was explaining these redshifts by an expanding universe, and we model these redshifts using the Doppler effect. This is something that we actually do in our studies. We get exam questions on it where it's okay, well, we can use Doppler effect. Now, the Doppler effect, we can model it using that. The mechanism is different. It's not necessarily that objects are themselves moving apart. It's that space is expanding rather than the objects necessarily moving themselves. Quite often you get the analogy of you're baking a loaf of raisin bread. So you put your dough in the oven with all the raisins in it, and then the dough expands. And as the dough expands, the raisins move further apart. So it's the expansion of the dough which is pulling the raisins apart. It's not the movement of the raisins through the dough. So that's an analogy that's often used. I mean, there are a couple of problems with that analogy. That it suggests, if you're thinking of the universe as being the dough, it suggests that there is both an edge to the universe and a center to the universe that the expansion is happening from. And that's not the case. The universe doesn't have this central point. You can't say, all right, here's the center that everything's expanding from. It's just that everything is expanding. Space everywhere is expanding. It doesn't matter where you are, you're not going to find a central point. Similarly, you're not going to find an edge. The universe isn't a lump of dough where you can just suddenly come up towards the edge of it and say, oh, right, okay, we've hit the edge of the universe now. That's also not how it works. So be careful with the analogy of the raisin bread. It's great for seeing how the expansion of space can pull things apart rather than things having to move through it. But don't get too carried away thinking this is a really, a more exact model of how the universe actually is. So yeah, I mean, this has really moved things in with this, discovery of the expanding universe, moved into all of the cosmology that then happened over, everything from then up until now. This is why he's one of the founders of observational cosmology, taking actual telescopic observations of the universe and then drawing conclusions and creating theories of cosmology and the evolution of the universe based on that. So yeah, really striking out into a new field. And this is bringing astronomy more into science. I mean, Hubble never won a Nobel Prize or anything like that, because back then astronomy wasn't considered to be really part of physics, certainly not from a Nobel Prize point of view. It was considered to be separate. And Hubble and other astronomers, as they were feeding more and more of this information into physics and having more of an effect on physics themselves, they were campaigning, this is part of physics. Astronomy is not a wholly separate subject. It's now been accepted by people such as the Nobel Prize Committee and such like, that this is now acceptable, is now meets the criteria for consideration for Nobel Prizes, but they don't award prizes to people after they've died. So Hubble's never going to get a Nobel Prize. It's too late for that. But he was instrumental in, really making astronomy taken more seriously as an actual science and how it can feed into serious theoretical physics. So, his involvement with the army continued in World War II. I mean, we can see here that he lived through World War II. And he did work as a civilian for the US Army during World War II, improving the design and performance of bombs and rockets and things like that. So, expertise in ballistics and aerodynamics and that sort of thing. So, and he had some good measurement techniques for really being able to analyze the performance of bombs and rockets. So he was still engaged in a military role there, but as a civilian. He was clearly going to be too old to actually be active during World War II as as military personnel. But yeah, he certainly made his mark as a scientist inside the military. So yeah, remarkable man, really. I mean, multiple talents both in science and other academic subjects and in athletics. Revolutionized the view of the universe and cosmology, and a real giant of astronomy and physics in general.